Yeah, so stasis, generally can't be used in vacuum environments, and there's a couple reasons for that. Uh, One, it's an electromechanical system, which means it needs, you need to somehow figure out a way to get power to it. So if you've got to run the cables to it, you got to run it through your vacuum, and it's kind of difficult to create seals to run electric cables through. But it's not undoable. The more important reasons are. One, if you're in a vacuum, we're dealing with stasis isolators that has electronics, and they also run at very, very high voltage. So when you take the air out of an electric system, you've got basically no dielectric, no resistance between places where there could be opposite polarity and have potential for electrical arcing. So we have a very, very high voltage used in stasis to expand and contract the piezos. And if you don't have air there to prevent arcing, the isolator will likely have serious performance issues. The other reason is stasis contains various components that outgas, like epoxies and rubber cables and wires and solder and soft spring-like components and things like that, which also outgas. So, when you put something that outgasses in a vacuum environment and you reduce the outside air pressure, it's just going to accelerate that outgassing. So what you'll find is if you're trying to keep a sterile vacuum environment, you put a high outgas structure in it, you have high potential of ruining your environment by accelerating that outgassing. So really, it's not designed for use in vacuum environments. What they did, they wanted to figure out how much it outgassed, so they put it in a vacuum to measure that outgas. So they intentionally outgassed it in a vacuum. So that's how the outgassing test works. But they were in a clean room environment, and they were concerned that the outgassing would cause problems with the clean room filters and whatever other operations they were doing there.